Right. Welcome to the panel session. In this panel session, we'd like to exchange views on the future of quantum science and technology with our distinguished speakers. I'm Eiji Saito. I'm here today as a member of the Quantum Phase Electronics Center called QPEC. So QPEC is a center which brings together the leading researchers in the field of quantum material and quantum computation and quantum information science to accelerate the research in quantum science at the University of Tokyo. Let's start. First, I'd like you to give a brief introduction to your research related to quantum science or your organization. So first, Akira, please go ahead.
I'm Akira Furusawa from University of Tokyo. Okay, this is my quantum computer. And this is quantum lookup table. That means superposition of all input-output relationship. So when we make quantum computing, we make measurement and select one input-output relationship. That is our quantum computer. So, and we are making this quantum computer by using optics. That is collaboration with Tetsuomi, NTT people. By using these, it is called squeezers. By using 4 squeezers and 5 beam splitters and 2 delay lines, we can build a very large scale quantum computer. And also, it is universal. And it is fault tolerant. And these dots correspond to qubit. And these between dots correspond to entanglement. So it is very large scale quantum computer. And also, it is very fast. Of course, we are using light beams for our quantum computers. As you know, carrier frequency of optical beam is more than 100 terahertz. In that case, you can have clock frequency of 10 terahertz. As you know, supercomputers' clock frequency is only several gigahertz. So it means almost 10,000 times faster compared to supercomputers. So in that case, without efficient quantum algorithm like Shor's algorithm, our quantum computer is really fast for all types of problems. And we are building a real machine. And next year, we will make it on the cloud. And hopefully, we can make a startup company next year. So it is very close, not a dream. Thank you.
Thank you very much, Professor Sensei. So next, Tetsuko, could you brief presentation on the
My name is Tetsuomi Sogawa, NTT Science and Core Technology Laboratories. And I also serve as a program director of Quantum Technology Application Project Cabinet Office. And my research background is non-quantum nanostructure fabrication, but as a director of NTT laboratories, I promoted many research projects on quantum technologies. Today, I'd like to talk about quantum technologies in ION, innovative optical and wireless network. I hope all of you know ION. No? Okay. So 4 years ago, NTT proposed ION, that is next generation network and computing platform. The most important framework is all photonics network, as shown here. We call it APN. APN provides end-to-end optical communication path without using OE and EO conversion in switches and routers. Therefore, APN drastically reduces latency and energy consumption. We have already started commercial service this year. I hope you understand this APN is very important to the future quantum network and quantum internet. And Furusawa sensei explained, we have been developing next generation nonlinear optical devices called PPLN waveguide, as shown here. The important performance is this device provide phase-sensitive amplification. This means only signal can be amplified without increase in the noise. And this device has very wide gain width, over 10 terahertz, which is 2 times larger than the conventional L.5 amplifier. These properties are very, very important to construct ultra-fast optical transmission system. And also in ION, wavelength conversion function is also important. Another important feature in quantum technology is squeezing, as Akira already introduced. And I move to another topic. This is collaboration work with Professor Katori. He is now planning to develop a nationwide optical lattice clock network, which deliver ultra-precise frequency and time standard instead of GPS. This figure shows the test bed of optical lattice clock network in Tokyo metropolitan area. Riken Hongo campus here and NTT Atsugi Lab are connected by 190 kilometer commercial optical fiber. NTT contributed the development of a repeater system installed in telecom station. This repeater removed the frequency noise caused by the vibration of fiber and reproduce a very fine frequency signals. We observed frequency instability is less than 1.1 times 10 to the minus 18th, even in the noisy downtown area. So we believe ION will provide a new network service which deliver ultra-precise frequency and times standard. Okay, thank you.
Thank you very much, Saito-sensei. I'm Tsuyoshi Yamamoto from NEC Corporation. I am a researcher at the NEC laboratory, mainly working on the superconducting quantum computer. But today, I want to introduce the quantum technology research and development at NEC. So this slide shows NEC's technology vision as a driving force for creating social values. And our goal is to contribute to the human society by solving social issues, making use of our technology, and creating social values out of it. And we think it is important to combine software and hardware technologies. And we believe that our strength is that we have been working on both technologies for a long time. As for the software technology, we have a cutting-edge artificial intelligence to enable to visualize and analyze and give prescription to the problems. And as for the hardware part, we have developed various ICT platforms, such as secure network platforms and computer system platforms. Yes, so, and for coming quantum era of quantum era, of course, we think the quantum technologies are important. For example, the quantum sensing is very important as a method to visualize the real world with unprecedented precision, a level of precision. And also, quantum cryptography enables ultimate secure communication, and quantum computing would qualitatively change the way of analysis because of its tremendous computing power. And we need to update our expertise with quantum technologies and incorporate them into our vision. And as for the quantum sensing, we are working on a small size, low cost atomic clock. This is similar to what Tetsuomi introduced as an NTT activity. And it's not as accurate as their clock, but it's small and low cost. So we are thinking to distribute in the society. And we expect that we use this as a position and a timing sensor and accurate enough clock. And we think that such accurate clock will realize various advanced and robust network systems in social infrastructures and will be used, for example, in self-driving car systems. And we are doing this in close collaboration with National Institute of Advanced Industrial Science and Technology, AIST, in Tsukuba. And as for quantum cryptography, we are working on quantum key distribution system. We have developed prototype systems for commercialization and successfully demonstrated 30 days of continuous operation through field fiber in Tokyo. And as for the quantum computing, we have been working on the hardware development based on the superconducting circuit system. And more specifically, we are developing a quantum annealing machine aiming to solve various kinds of optimization problems which exist ubiquitous in the society, but also known to be very difficult to solve when the problem size becomes large with the present computer. And as a future long-term technology, we are also working on the fault-tolerant quantum computing, aiming to enable the scale-up integration of the superconducting qubits far beyond what is currently achieved, say 100 qubits. And this work is also done in collaboration with AIST, but also many other groups under the national project, Novo project, and also Moonshot project supported by Japanese Science and Technology Agency. Finally, as for the relationship with the University of Tokyo, NEC and 4 other companies have started social cooperation program in March this year to promote the development of quantum native students, which we think is very important task in the coming quantum era. Thank you very much.
Thank you very much. and thank you very much for this arrangement. I'm very honored to be here. So I here represent the Novo Nordisk Foundation, where I serve as Senior Vice President. So my background is as a professor of physics from the Niels Bohr Institute, but I've worked for the last 4 years at the foundation. Also, I am the chairman of the board of the Quantum Foundry Copenhagen, which I will return to in a second. And I am a member of the World Economic Forum Global Council for Quantum Economy. And so with this background, I'd like to represent today what we do, what we support from the foundation side in Denmark, and how we can also envision collaboration with Japan, which is definitely on our wish list. So first of all, about the foundation. So the Novo Nordisk Foundation is a Danish enterprise foundation, which is a special Scandinavian concept where foundations own companies. And so the foundation is a charitable foundation, although we do own for-profit companies. So the largest ones of the companies which we own is Novo Nordisk. So Novo Nordisk has a division, a very successful division in Japan, and already through that, actually, we do have established a close collaboration with Japan, which we highly, highly value. So the companies which you see below here, there are actually 160 of them. The dividends from the companies go to holdings, Novo Holdings. The dividends go to the foundation. And then us who work in the foundation, we use part of this to support research and also to support social and humanitarian purposes around the world. So a few words about the foundation. So last year we granted 1 billion euros, and we are definitely exceeding that amount this year. The total assets of the foundation, now actually that number is outdated, it's closer to 130 billion euros, which makes the Novo Nordisk Foundation the largest private foundation in the world measured in terms of assets. So our strategy has 3 pillars. One pillar is the health pillar, which I think comes natural when you know of the companies which are under the hood. The second, which is actually new, only 2 years old, is sustainability. And here we have very important initiatives, and we are increasing our activities in the sustainability area. Third, and importantly for quantum actually, we have what we call the life science ecosystem. So this is where we support fundamental research, innovation, teaching, and outreach to the general public. And so quantum we see as a really important technology which is going to totally transform both health and sustainability. Therefore, seen with our eyes right now, it's in what we call the life science ecosystem, but with really important applications both in health and in sustainability. So in quantum, we have made, I would say, significant investments at this point. So I'm only bringing up one example here, which is within what we call the Novo Nordisk Foundation Quantum Computing Program. So for this, we have granted 200 million euros for the first 7 years, and we definitely expect it to have a longer lifetime. Now, one thing which is really important is that development of quantum technologies take time. So it's not something which can be done on the time scale of, say, 3 years. One needs to be very patient. And that's, I think, where the pharmaceutical background may help, because in pharma, it's also normal to have a very long time scale, be patient with the investments. And this is what we are as a foundation in quantum. So the mission we are on is to develop quantum technologies to solve real problems in the life sciences. So we have identified that one of the most important challenges for developing quantum technologies is to have control over the quantum materials, really at the single electron or single photon level. So for that reason, actually, our largest investment is in this Novo Nordisk Foundation Quantum Computing Program, where focus for the beginning of the program is on the materials. So we have done something which is, I think, a first-timer in Denmark at least, is that we have divided our grant into one part, which is a classical academic research center, and into another part, which is a limited liability company, which we called Quantum Foundry Copenhagen. Now, the reason we did that actually was exactly for the reasons that both the president of the University of Tokyo and also the Prime Minister of Denmark said, namely that quantum is special, seen in a geopolitical context. We need to be somewhat more protective towards our technologies. We need to choose our collaborative partners with care and have trusted partners. And that we can do in this setting, which we have constructed here. Also, we are trying to learn from history within semiconductors. The reality is that although Europe was in many ways leading within research, leading to what we today know as microchips, Europe totally lost out and now essentially is not a part of the supply chain for microchips. So now this time we're trying to be smarter. We're trying to, from the beginning of development of technologies, to be more protective, to choose our partners wisely, to be able to enter into collaborations with selected partners. And that is highly important. And this center here is exactly constructed because we know there's no way this center alone can develop a fault-tolerant quantum computer, which is the goal of the center, actually. That's a major goal of the center. But with the right partners, that is indeed possible. And that's why the partners of this center are chosen internationally and could also well be from Japan. And we are definitely open for such strategic collaboration. So regarding Japanese-Danish collaboration, there is, of course, the very likely possibility of having strategic collaboration within selected areas. Also, there's a very excellent opportunity actually of establishing student exchange programs, which is something that we would certainly like to support also from the foundation side, because it's a good way of starting collaboration between two countries and also to strengthen the existing collaborations, which we fortunately already have. So with that, I think I would like to say thank you.
Thank you very much, Lene. So, Yang, so could you share your view on the news points?
Yeah. Thank you. Yeah, I will probably share a little bit of what happens in on the Danish quantum scene at the moment. And again, thank you very much for the invitation. It's fabulous to be back in Japan again and speaking to all our colleagues and all the fascinating physics that is going on and science and startups that we hear about. What I would like to say and bring to your attention a little bit is what is sort of the overview of the Danish quantum scene now told in 5 minutes. So forgive me if I'm missing out a few pieces here. But despite that Denmark is sort of a small country of only about, I think it's 6 million people, something like that, we have quite a substantial activity level on quantum technologies that we would like to share with you. One of the things that we could bring forward here is that already in 2022, there was a $404 million investment total in quantum technologies. And if you look over average sort of per year, we are about a level of $157 million, which is not too bad, given that we are not too big a country. Allow me also to bring into to play industry here. We call it an emerging quantum industry. We might even also, given the comments given by the Prime Minister, say that it's an accelerating quantum industry that we have present here. And we have a number of representatives here today that you can talk to. They are both in quantum software, they are in quantum security, you will see them in quantum materials, they will be supporting technologies that you would have here. You would have a number of activities going on there. And this is sort of a small potpourri of some of the companies that we have in Denmark on this. Another important thing that is going on in Denmark right now is that a lot of companies would like to establish themselves within our ecosystem, which we are really happy about, and we would like to talk to people from Japan also in that respect. And I can say here, last month we had 4 newcomers to the Danish ecosystem. Mabel was one of them. We had River Lane and Quantum Exponential as another company that was setting up in Copenhagen, and they were particularly proud about having QAnsys, that is a Japanese company, establishing an office in Copenhagen that we would like to work with for sure. Allow me also, I will not say too much because Lene, I think you already told about the NQCP, the sort of Novo Nordisk quantum computing program, which is a major investment. I would say in Denmark, another thing that I would like to bring forward is the strong base, the strong scientific base that we have in Denmark. I counted up here before going here to Japan, where we have more than 24 centers of excellence, 487 scientists working on science, quantum science broadly in Denmark. And I would say we cover all different areas from quantum sensing to quantum computing, quantum materials to quantum information as well. We have recently a strategy that's been launched from the Danish government side in 2 parts. National Quantum Strategy that targets both sort of basic research, the pipeline into new sort of companies, and then also innovation, and on top of that also the bridge between sort of laboratory to company. And there is an investment currently of about $171 million for that in the period of 2023 to 2027. Another program I would like to bring forward is another Novo Nordisk program that is targeting sort of quantum for life sciences. We have a number of programs there, and I think they will be augmented also during the coming years here, targeting sort of quantum simulators for big biological molecules or biological systems, and several representatives from the professors here in the audience from Denmark are active within these programs, which is, in my view, an interesting venue also before we have the full tolerant quantum computer operating. I think that could be an interesting thing that we should look more into perhaps than we do right now. I have put here Danish quantum community, which is a strong community among Danish people who would like to bring the quantum agenda forward. I bring this point up because I think one of the other things that are really strong in Denmark is the tight and close coordination and collaboration between government, ministries, industrial branches, industry, startups, foundations, academia institutions, and universities. And this is one of the things that, in my view, have allowed us to move very fast forward on the quantum agenda. And the last thing I would say here and bring to your attention is, of course, also that Denmark has been selected for hosting a Diana NATO Center for Quantum Technologies in Denmark, which is increasing also the sort of overall ecosystem for the Danish side. So I think this is just to give you a taste of some of the things that are happening in Denmark and give a good basis for further collaborations between Japan and Denmark. Thank you.
Thank you, Jan. So finally, Ulrik, so could you make a short presentation on your scientific work?
Thank you so much. And I will also start by expressing me sincere gratitude for inviting me here at the University of Tokyo. I mean, one of the most prominent universities in the world. So, and I also personally enjoyed a lot of collaboration with scientists here at the university, in particular with Akira Furusawa, with whom I collaborated for almost 2 decades by now. I remember back in 2005 where we together implemented the first single mode and 2 mode quantum computing gate. But that's many years ago by now, and fast forward, we are now here. So I'm going to, my name is Ulrik Andersen. I'm a professor at the Technical University of Denmark at the Department of Physics. And I'm going to say a few words about what I work on in my research team. There's a photo of the team here of about 50 people. So this is just like zoom in on one activity in Denmark. I mean, there are many more activities, as Jan also mentioned, in Denmark. Some of them are also represented here by professors. I mean, Peter Lodal is here from the Copenhagen University, Leif Oxenløve from also from DTU is here, and also Jørgen Ellegaard Andersen from University of Thomsen, Denmark are here, representing different activities in Denmark. But here I'll just zoom in on one activity. I mean, a bit biased, I mean my activities, of course. And so what we want to do in my research team is that we want to explore quantum physics in the microscopic domain. So we want to see what happens when we increase our system size. I mean, we have many particles, we have many modes, we have heavy systems, and then we're trying to explore quantum physics in that regime, and then explore this knowledge to develop new quantum technologies, applications in sensing, communication, and computing with the aim of demonstrating a practical quantum advantage, which is super difficult. I mean, quantum advantage has been demonstrated, but really demonstrating a practical quantum advantage is something that is difficult and something that we're working on. We make use of 3 different physical platforms, complementary platforms in my research group that you can see here on your right-hand side. So we use photonics, so we generate entangled light, squeezed light, as Akira was introducing you to. And we use this for quantum communication and sensing and computing. We also use color centers in diamond, a field that is also very active here in Japan. So here we are able to find a single electron in an ocean of billions of electrons and then control this electron at our own will. I mean, have it as a qubit, controllable qubit. And this can be done at room temperature, at normal pressure, and without any shielding. So this is a fantastic material, and you can use this for quantum computing if you are able to scale it up. And you can also use it, as we do, as a quantum sensor. So it's a very good quantum sensor for sensing, for example, biological activities. We also, the last platform we are exploring is macroscopic mechanical oscillators, where we make these membrane oscillators. So these membrane oscillators can be used as a bridge between the photonic regime and the solid state regime. And we're trying to develop these membranes with exquisite quality, so that if you poke them, they will keep swinging for more than an hour. So really, really high quality. And then, as I already mentioned, our aim is to use these technologies or our knowledge in realizing a practical quantum advantage in sensing, computing, and communication. And here, just 3 examples on the bottom of my slide. So on the left-hand side, this is a macroscopic image of a biological system using entangled light. So by using entangled light, we can improve the sensitivity, we can improve the resolution, and we can improve the speed of taking such images. And this is one example from our laboratory where we are taking an image of a biological system. In the middle here, we are developing these large cluster state that Akira was introducing you to before. So we are also developing these cluster states in our laboratory, and we have used those cluster states. So these are like the substrate for one type of quantum computing, and we use this substrate for implementing quantum computing gates. And we have implemented, or we have proposed a complete blueprint on how to use this cluster state, including universality and including fault tolerance for quantum computing. Okay, and then lastly, we also have a lot of activities on quantum communication. So we use non-classical states of light, or also using a standard coherent state of light for realizing quantum communication schemes, for example, generating secret keys in a network. So here in Tokyo, you already made a fantastic quantum key distribution network in the metropolitan area. And we are actually working on exactly the same in Copenhagen, try to set up a network, which is a collaboration between many universities in Denmark, where we're trying to set up a network, a secure network in Copenhagen, but also coupling Copenhagen to Odense in this network. I think that's all what I want to say. Maybe I should mention at the very end here that the foundation of all this work is our Center of Excellence, which is kindly supported by the Danish National Research Foundation. And then, as you also mentioned, we also get support from the Novo Nordisk Foundation, of course. Thank you.